Thank you.
Thank you. Now, what does this feel like? Does this feel this chair sitting here? You know, a little bit of Clint Eastwood today. That's good. Well, Heather and I are going to try and rotate through this. We're going to talk for about an hour and a half in sort of 3 different sections. Hopefully, there'll be some time for questions in between those little sections. And theoretically, we'll be able to actually sit in this chair. So I'm a little taller, Heather's a little shorter, so I'm not sure how this is going to work, but we're going to give it a try. We want to thank our sponsors for this work. Historically, they've been the Northwest Energy Efficiency Alliance and the U.S. Department of Energy, of course, the University of Washington. This is our lab space at the University of Washington called the Integrated Design Lab. We do a lot of research and technical assistance related to various building types, daylighting research, and a lot of technical assistance in healthcare. We also wanted to thank the various folks from here for bringing us here. It's an honor, and thank you for coming tonight. One of the reasons that we're talking about this is, and one of the reasons it was interesting to the Northwest Energy Efficiency Alliance, was that healthcare consumes roughly 5% of our nation's energy resources. I mean, healthcare, think about it. On a worldwide basis, because we're such a huge consumer of energy resources, us in Canada, in the world, this equals about 1% of the world's energy resources consumed by healthcare buildings. I mean, it's crazy. It's really crazy. But it's a huge opportunity. And just to present this within some context, there is a sea change happening in healthcare right now related to energy efficiency, heating, ventilating, and air conditioning systems. Building envelope systems is a part of that. And we're here to sort of have a discussion about that. And we hope that you'll ask questions, that you'll bring up difficult questions, difficult points of view. I want to say just in the beginning that we do a lot of work related to performance in many different buildings. We specifically are concerned about daylight, view, energy. We know that our work dates back about 40 years in daylighting buildings. We had the first artificial physical model simulation lab of daylighting in North America, built in the 1970s. One of the reasons it's important, it's certainly important in healthcare, related to healing, related to staff performance, retention, being healthy in the physical environment, is that there has been a sea change in vision and light in the environment. Have any of you read this article from Scientific American? It's a great little piece from May 2011, and really just is the tip of the iceberg related to these issues. Basically says that vision was one of the first sciences related to the human body that we felt like we really understood. By about 1820, you know, the science of the eye, the science of the optic nerve, and how that information was treated within the brain, you know, within reason of 1820, felt like, okay, we understand this, we'll put it away. You know, there was work done along between 1820 and 2010. But in the late 1990s to the early 2000s, a number of things were started to be noticed about different people reacting to light who had no vision, and differences in their behavior, differences in their health, and a whole new look was given to this science. And we discovered, if you know the optics of that, the ganglion cells, the retina, and the rods and cones, so that it was thought that the light was perceived along the retina by the rods and cones. It was just the ganglion cells were just connectors, nerve connectors to the optic nerve. And it turned out the new science in the last 7 years has shown that the ganglion cells actually are light receptors. And they're receiving light in the very blue shifted range, and they're affecting all sorts of hormonal balances within our body. And so a science is really developing around that and how unhealthful it is to move us away from access to that light, which is the sort of laboratory science that we needed to begin to indicate why we actually need windows in buildings and why people might get healthier. Yes?
So that was based on people who were born for it?
You know, you need to read the article. It was about a year ago that I read this article. I don't want to speak unintelligently about it. But it really started with this work with people who had sight and didn't have sight, and light seemed to be affecting them. And it's interesting. So daylight in buildings, extremely important. Our Target 100 project is what we're here to talk about today, which really is a small piece of this work related to performance in buildings. Target 100 really is an outgrowth of hundreds of people in our communications with them around the United States. It started in 2006 in the Pacific Northwest. Again, roughly a 50-member peer group of hospital owners, large contractors like Turner. A huge debt of gratitude to Turner Construction for a lot of our costing work, which was done through TBD consultants, and a great relationship with Turner. So these have been a great piece of work that has really brought in many, many, many points of view from, as I said, owners, contractors, architects, engineers, facility operators. This project has used as consultants Solarc Architecture and Engineering, as I mentioned, TBD consultants, and NBBJ. Started in 2007 with NBBJ. They had a Sustainable Healthcare Energy Challenge, and we were partnered with them through another alliance that we had with the Northwest Energy Efficiency Alliance. And we were looking at energy in hospitals. Nobody really had looked at that in 2005, 6. And we thought we had a pathway for them, so we partnered together, and they've been a great partner ever since. This project has gone on by the U.S. Department of Energy for the last 3 years through an initial set of workshops and peer review meetings that happened in the 5 cities outside of Seattle. Then an analysis of new energy models, cost models, performance models, then a second round of workshops. And we're in the last throes, in the last 3 months of this project, beginning to develop the communications around these outcomes. The goals for the project were to find out what it took to meet the 2030 challenge for between 2010 and 2015. We all know what that is, maybe not. That's to beat a baseline performance standard developed by the Commercial Building Energy Consumption Survey, and later a modified database of hospitals within the last year. So we're looking at operating hospitals, or operating buildings, a cross-section across the United States that is climate specific, and between 2010 and 2015, Architecture 2030 asks us to beat that baseline number by 60%. So our goal was to beat that goal, make that goal, 60% improvement with no additional capital cost to the owner. Huge goal. And we met that in Seattle, and we thought that we could meet it in the other 5 cities. As you can see, Chicago, New York, Houston, Phoenix, and Los Angeles, and very diverse climate zones. Heather will go through more of this as we go through. Should say that the metric that we're using, that I'm sure all of you are familiar with, is energy use index, or energy use intensity. It's like miles per gallon. The units here are thousands of BTUs per square foot year. The European unit is kilowatt hours per square meter. Typical hospitals in the Pacific Northwest, it turns out typical hospitals nationally consume roughly 225 to 350 kBTU per square foot year. That's very common. You see outliers at 450, 500, 600, and you see some that are way below that at 150 or 100 for very specific devil in the details sort of reasons. A new hospital to code, this one 2004, is going to have an EUI of roughly 200 to 250. The 2010 code that we're going to show you, is right in the same range. Most of the loads in hospitals are not code regulated in terms of energy code regulated. Therefore, the energy code isn't driving these down. And it turns out, as a total share of energy use in buildings, hospitals appears to be going up. And one of the reasons we think is because so much of the energy use is non-code regulated in hospitals. Typical office building in the Pacific Northwest consumes 70 kBtu per square foot year. You can see that in that range is 3 to 5 times as much energy is consumed by a hospital as an office building in common use today. We have I should say, we're moving into the new Bullitt Center by the Bullitt Foundation in about 3 months in Seattle. It's an urban 6-story office building and will be the most energy efficient office building in the world for an urban office building. It has an EUI of 16 and is net zero energy. Will produce all the energy it requires on an annual basis that it uses. So 16 versus 350, that's a range. So the way you access these numbers is through Target Finder as a baseline and for your goals. Easy to find Target Finder, just Google Target Finder. You find the little green button that we see up here. You can press that button, it'll ask you some fairly simple questions that you're probably capable of answering or can find out answers to within a day. And then it will produce some baseline information for you for that median building in your climate region. Here are Seattle, Chicago, New York, Los Angeles, Phoenix, and Houston. And there's been a little glitch in this process over the last 3 years. And that is DOE and EPA were very concerned that their database was very small for hospitals. And it was archaic. It was from the Electrical Power Research Institute. And so they reached out to hospitals and said, will you give us information on the energy use of your hospitals? And over the intervening time, 2010-11, they developed a new database. So we had a new baseline. And that's what these blue bars versus gray bars are. This is a vertical axis of EUIs in kBTUs per square foot year, 350 here, 0 here. You can see that here we are in Seattle. The average hospital in 2010, before the change, was 271. The average hospital today in this new database is 249. And you can see some variability here, New York being the lowest. Of course, the New Yorkers said, yes, we know we're the most energy efficient folks in the entire country. And we're sort of from the left coast, and we're like, you're kidding, right? Really, honestly. And we think there's some interesting reasons here, but as Heather will mention, when we run hospitals in your region through Target Finder, they show equally low. And we have some suspicions that there's a lot of district heating and cooling that's going on, certainly in Manhattan and around here, and the way that those numbers are counted at the source versus at the site, at the property line, and the heat or cool that goes across that property line, we think drives these numbers down a little artificially low. We think that what you ought to get from this is nationally, this is about a 250. And it really doesn't vary by climate. And that's because these are such internally load dominated buildings. And our problem is to see if we can offload, take out some of that internal load, and when we start to make them more climate specific. When we can pull out that load, which we'll show you how to do, all of a sudden, the building in Phoenix looks a little different than the building in Seattle versus the building in Boston or New York. So just as a simple idea, Target 100 came from our original work that Heather will talk about as a 60% reduction from 250, roughly. That's our 60% reduction to meet Architecture 2030. And we think it's a good goal based on sort of this general average for the entire country, Target 100. And it's a nice round name. And I think we're actually using Targeting 100.
Targeting 100.
Yeah. These are some of the folks that we represented by the names of their companies. And we have seen multiple people from the same company in our peer review meetings around the United States. But we want to really thank these folks because they've been a great gift. They've really changed the course of our research over time. And we did things that we wouldn't have otherwise done without their input. These are our 6 cities that I mentioned. These are our pictures from our workshops in those 6 cities. A great group of people, generally the greatest innovators in their region, came to these meetings. I want to say just before we start with Heather's presentation that in the process of building towards this project, we were really concerned whether our energy model for our first work between 2006 and 2009, there was a basis for all this, made sense. Now we felt like we needed to calibrate this model against reality. So we found a hospital, Legacy Salmon Creek, I think completed in 2004, right? Five, okay. And they had a great digital control system that would give us good sub-metering. And then they had a boiler system that also, because heating is our primary energy use, as you can see here, gave us separate information from dedicated boilers for different uses, end uses. So we went in and sub-metered this for a couple of months and then took that data that you can see on the right and compared it to the information that came out of our models. I should maybe step back a second. There's a piece of slide we don't put into this, but it's worth saying. When we first started looking at energy in hospitals, we didn't know what the problem was. We thought, well, what do? Do you have to move the MRIs into a parking lot and put them in a separate building or something? We really had no idea the energy end uses, disaggregated. So we started looking around, finding information, and what we found out is that the primary energy use in hospitals was for heating. And it was dominantly in a building that almost doesn't need heat because of the amount of energy input would seem to indicate that the amount of energy being used in here, and most of it being given off as heat, that it wouldn't need heat. But it was primarily using gas for heat. And it was, as this slide can show, it was for reheat. And those of us who love reheat is that thing where you have a really big zone. It's cooled to the temperature that you're needed on the sort of interior parts of the zone. Parts of the perimeter zone then need heat because it's too cold and you reheat it. So you're cooling it and heating it. And if you're in a humid climate like you are in the summer, you're using that cool to drive the humidity out, and then you're reheating it to make it, comfortable. So I always think of when I'm in a hot, humid climate and I'm in a cold room, they're actually saving energy because they're not using reheat. So anyway, here are the slices that you can see. Fossil fuel is a little over 50%. You can see some of it's for process heat, some of it's for service hot water, some of it's for reheat. The service hot water was a really interesting one. In our original model, I believe it was close to 10% of the end use. And we heard from everyone who operated hospital, like, 10%? Really? That doesn't make any sense. Yeah, and here's how much it is in Legacy Salmon Creek, 1.7%. So interesting little piece of this, the MRIs. Remember me mentioning MRIs? Here's imaging, 0.8% of the total. It's about equal to the elevators. So the story gets more interesting and more complex. The system strategies for Legacy Salmon Creek, they had disaggregated heating, as I mentioned, related to the individual boilers. This was a VAV, variable air volume air handling system. They had variable speed, ultra-efficient centrifugal chillers, and variable flow hydronic systems throughout. So this was a pretty good state-of-the-art building in the early 2000s. And actually, for the entire country today, it's probably pretty much the state-of-the-art. In fact, we have a building like this that we'll mention at the end that we've done technical assistance on that's actually running at 130 EUI that we think is a real leader. It's on the cover of the Advanced Energy Design Guide for large hospitals. So Legacy Salmon Creek, here's the fuel use. You can see reheat. That's that big red chunk. This is just a little calibration issue. This is our potable hot water. This is what we were showing in our sub-metering. And you can see 3 distinct peaks. This is the morning shower, which turns out was huge in our model, but almost non-existent in today's hospital. What we heard is, if you're well enough to take a shower, you're well enough to go home. Sound familiar? Yeah. So this is cooking, right? 3 meals. It's all the kitchens. We did a really interesting study related to interior lighting to find that most hospital patient rooms are illuminated at somewhere around 1.5 watts per square foot. The actual code today is, I think, 1.2. But the actual energy use in a patient room that we monitored half a dozen patient rooms over several weeks, is about 1/3 of a watt. So there's a lot of lighting in a patient room, but it's just not used very much. again, the sort of general other loads we can see here that I've sort of identified individually. So Heather is going to enter into the real nuts and bolts of Target 100.
Perfect. Thanks, Joel. Ooh, can you guys hear me okay? Okay, good. I just wanted to make sure that lavalier is in the right place. So please feel free to jump in with questions if you have them along the way. I'm sure you will. I'll try to make this as clear and succinct as possible. So as Joel mentioned, the goals for Targeting 100 are to meet the 2030 challenge. We wanted to see if that's possible in a hospital. What would it take to meet the 2030 challenge? How much would it cost? Is it going to be 30% more? Is it going to be cost neutral? And then disseminate the results. So the third piece is part of why we're here. We are really interested not in just the research, but the implementation. So getting real hospitals built that are meeting these aggressive energy targets. So on the right here, we see why it's called Targeting 100. Joel talked about this a little bit. The national average for a hospital is 250 kBTU per square foot year. 60% of that is 100. So we're targeting an EUI of 100 kBTU per square foot year. And coincidentally, or also part of the name, is that if one were to apply for an Energy Star rating, you would probably get an Energy Star score of 100 if you met that energy goal. So targeting 100, that's where the name comes from. And we're looking in 6 of the largest cities in the US, and they were chosen because they're in the most diverse climate regions with the biggest population centers within those climate regions. The way that we set up the research is trying to keep as much constant as possible, but also looking at 2 architectural schemes. You'll see those 2 architectural schemes at the top. The one on the left is pretty plain, really deep diagnostic and treatment podium or platform with a podium on top of patient towers. We see this typology a lot, maybe not in this simple of a massing, but it's pretty typical in healthcare to have that really deep diagnostic and treatment block. As Joel mentioned, we're very interested in looking at how we can incorporate more daylight view potential for natural ventilation into the hospital morphology. So the scheme B on the right, the more perforated model, has a lot of interior enclosed courtyards all the way down through the diagnostic and treatment levels, also in the patient towers. So there's a lot more access to daylight, ability to see outside, go outside, and with transparent kind of bridge-like corridors that span between the 3 kind of separate towers. We worked a lot with NBBJ on making sure that the program that we had matched between those 2 schemes and that it fit within Scheme B specifically, because you might look at that and think, is there any way that the program can actually fit diagnostic and treatment in that perforated of a scheme? And we did a lot of work on that. I'm not going to show it today, but it'll definitely be part of the output of this work, because we really wanted to make sure that this is a workable model.
You know, one of the things that might be interesting is these do fit in approximately the same footprint. So it doesn't require it to be in a suburban environment to be more daylit. And Scheme B does have 50% more skin to it. So it's an indication of cost implications as well as environmental performance.
Yeah. So as I mentioned, we tried to keep the program constant, and it's a 225-bed program, 477,000 square feet. And as Joel mentioned, the window-to-wall ratios are constant between the 2, but Scheme B has 50% more skin. So there's more windows, more walls. So that comes into the cost model. Footprint's the same. And then what we did is we kept the energy bundles the same under the 2. So we wanted to see what's the energy implication between these 2 and what's the cost implication. We'll talk about that more as we get to the results. So each of these 2 architectural schemes has 4 energy options. The first simply is the baseline. So if you were to build it to code today, these are the strategies you would probably use. And then 3 high performance options. And I'm going to walk through each of these options to lay the groundwork for what we were looking at. But essentially, we're grouping them into architectural strategies, building mechanical, so how the HVAC is distributed, and then the plant systems, the central plant systems. And really, the 3 high-performance options only vary at that central plant level. The building mechanical and the architectural systems stay constant. So it simplifies the matrix a little bit. But I do want to say that even though we're grouping these categories as separate, it's really important to the fundamental basis of this project that these are grouped, bundled strategies. They all work together as a whole to meet the energy and cost goals. So I'm going to walk through that a little bit. We think that it takes integrated strategies, and it also takes an integrated team to be able to work together to achieve these goals. So some of the examples of how that plays out in Targeting 100 is in this example. So we want to reduce the solar gain on the envelope. And really, the envelope becomes part of the cooling system in that sense. To the right of that, the pointer here, this is just a little wall section with exterior dynamic shades. We'll talk about those being incorporated into the Targeting 100 high-performance models. What this is it's an annual loads graph. So on the left is January through December, and it's looking at the load profile of the building. And what we can see is in green is the high performance, and the blue is the baseline. What we're trying to do is minimize the peak, which means reducing the size of the equipment. And we also want to reduce the area under the curve, which is the amount of energy that's going to be used on an annual basis. So there's both reducing the peak and reducing the area under the curve. And these solar shades help us reduce that peak. And what reducing that peak enables us to do is use different types of ventilation systems in the patient rooms and other spaces throughout the building. I'll talk a little bit more about this a little bit later on, but in Targeting 100, we're using displacement ventilation with decoupling the heating and cooling from the ventilation air using radiant panels, ceiling panels, and radiant heating panels at the window. So reducing the solar gain enables us to reduce the load, enables us to use different systems, which thereby reduces the area under the curve, so the annual energy use. It also is a smaller system, so we can reduce the floor-to-floor height minimal, like by a foot or 2, or it gives more flexibility in the floor-to-floor height. And then we can use systems at the plant level, like ground source heat pump plants that are sized appropriately. They're smaller than they would be if we hadn't used these strategies. And the loads are balanced. The heating and cooling loads are balanced on an annual basis. So that's just one example of how we're integrating architectural, building mechanical, and plant systems. So they all work together. There are cost adds, cost deducts. It all is part of the same integrated strategy. So now I'm going to walk through the various strategies. I'm going to start with architecture, the foundation of the energy bundles. Let's see. Yeah. So what we did with our cities is we essentially grouped them into northern climate zones and southern climate zones for the envelope. And throughout this presentation, when I'm just talking about, mostly about the results, I'm going to be referencing New York. Since it's closest to here, we didn't look at Boston, but I'm going to reference New York. So along the way, you'll see data related to New York. So in the baseline models for the northern climate zones, we used Zone 5, ASHRAE 90.1, 2010. And high performance, it meets or exceeds that. And everybody always asks, what does that mean? So this is the envelope specification for that. And I'm not going to go through the numbers here, but something that's important to point out is that we're really interested in performance-based metrics for Targeting 100, so meeting a performance-based goal. That being said, we had to choose specific products because we needed to build a cost model. So we had to put a stake in the ground and say, we're going to use, for the high-performance model, for the northern climates, solar band 60. And so we have the performance metric above for the envelope, and then the products below, making sure the products meet the performance-based metrics. So architectural systems more generally, high-performance envelope, we just talked about that. Solar control, I talked about that a little bit in the integrated systems. So we've said the high-performance models have exterior dynamic shading on the west, south, and east facades, but not the north. In some climates, the sun does creep around to the north, like in Seattle, but we decided we're just going to keep it on the facades that get the most sun. And we'll see the implication of that a little bit later in the results. And then, of course, daylighting. We're trying to increase the amount of exterior connectivity to daylight, and where possible, turn down or off the lights when there's daylight present. This didn't have as dramatic of an effect as we would hope. Many of the perimeter zones are patient rooms, and we decided not to incorporate daylight dimming in patient rooms. And we saw from the data that Joel showed how little the electric lights are actually used in patient rooms anyway. So there's a modest reduction for that, and I think there's room to grow in that area. So now building mechanical. This is where it gets a little bit more complicated. So for the high performance models, I'm just going to go back for a second. The building mechanical also is the same for the three plant option 2, 3, and 4, all the high performance options, and different for the baseline. So on the left here is the baseline. We assumed overhead mixing, VAV, 6 air changes per hour for the patient rooms minimum. In the ORs, the more highly regulated spaces like ORs, ED, kitchen, it's a little bit different. It's higher air change rates. So we followed the code for these things, and basically did it at code minimum for the baseline. For the high performance model, in the patient rooms and many other spaces, the lower, so not the ED, not the OR, not the kitchen, but the other spaces, we use displacement ventilation with radiant heating and cooling panels. So I'm going to talk a little bit more about what displacement ventilation means. And the work that we did in the Pacific Northwest prior to this work, we did not incorporate this because it had not been approved by NIH. Since that time, Farhad Mamarzadeh has decided to put his stamp of approval on displacement ventilation for healthcare. And there are several projects under construction now that are incorporating this strategy. And we worked closely with Mazzetti, Nash, Lipsey, Birch, and Stantec to make sure that how we were laying out the patient rooms and the air change rates and the technical details were sound in this work. This is a slide from them, which I find pretty interesting. So I'm just going to let this run. But on the left, you can see this beaker of an example of an overhead mixing system. So essentially, the air is just relying on mixing around and then eventually is exhausted. In displacement ventilation, the air comes in low, so like water, it comes in low, and it uses the natural piston effect of the air warming up, and it is evacuated high in the space. This video is an example of a patient coughing, and it's unfortunate that it's red, but it's a patient coughing. On the left is the overhead mixing system, and on the right is the displacement ventilation system. Beyond the delivery of the air, the difference is on the left it's 6 air changes per hour, on the right it's 4. And so what this study shows, one thing that this particular video shows is that the caregiver doesn't get surrounded by a cloud of aspirated gunk from the sick person. But it also, the study generally shows that the air in the displacement ventilation system is cleaner. So the particulates are evacuated more readily than in an overhead mixing system. So we think that it's a healthier environment and it uses less ventilation, which thereby uses less energy and smaller equipment.
You know, it can't be emphasized enough. One is everything we're doing is to code, so we're not breaking any rules. And more energy efficient actually means healthier. So that's one reason there's a sea change going on, is that we want the one on the right, and we're going to use less energy getting there. And that's a fantastic message to ownership.
The next slide is showing why an integrated approach is really important with displacement ventilation. On the left shows a window that is not protected from solar gain. So direct solar radiation can hit the floor, and that disrupts the natural piston effect of the air, and the air does not evacuate as well. And you can see how that happened. The green represents the air. On the right, the solar gain's mitigated and it works like we saw the person coughing. It naturally goes up. So that is another reason why it's really important to put these exterior dynamic shades, because it is in order to have displacement ventilation, you have to mitigate the solar gain. So there are two things that go hand in hand. Something that I haven't represented in a slide, I'm just realizing, that I think is really important is that we had a half-day kind of patient room design charrette with the people that we thought were the most important to making sure this would work. So where does this displacement ventilation supply go? Where does the return go? Where do the radiant cooling panels go on the ceiling? And where do they go on the wall? And we knew how many square feet of radiant cooling panels we needed. But we also know there is a lot of effort and kind of jockeying for real estate on the ceiling in a patient room. So we wanted to make sure, are we being realistic here, that we can actually put this square footage of cooling panels on the ceiling. And we started the day, we had folks from Mazzetti there, so engineers. We had architects and medical planners from MBBJ. We had lighting designers from Candela, Sparling. And we started the day with that group pretty skeptical. Like, no way it's not going to work. No way. And by the end of the day, we came to a consensus. It is going to work with lighting, bariatric, curtains, and the radiant cooling panels, and then the heating panels on the sidewall. And we came to a consensus where those things would go and created reflected ceiling plans showing those zoning. So we were really happy with the results of that, and we wouldn't have gone forward with that strategy if it was just out of bounds of being possible.
So the supply air, we should say, is at the foot of the bed, low, about 12 inches off the floor, so nothing can get in off the floor. And the return is directly over the patient's head.
There. So we thought at first, it's right where the exam light would be, right? But there's a way to zone the exam light so it's not right over the patient. There are two side by side, or an option where the return is a little farther back and the exam light's a little farther forward. So it was pretty exciting to come to a consensus on that, I thought. So the plant system. So as I mentioned, this is where things vary between the baseline and high performance options. So I'm going to walk through them with diagrams pretty quickly. So this is the traditional baseline plant. Essentially, the boiler and the chiller are separate entities. They're not connected. They're often simultaneously running using the cooling tower for the chiller. And that's how a lot of plants are built. This is the high performance plant 2. So, and I'm going to back up a little bit. This is a little bit of history, but I think it's important. When we started this project, we thought we're going to do a baseline, and then we're going to put the stake in the ground as far as we can and get as energy efficient as possible. So we designed 2 plants. And subsequently, through the conversations that Joel mentioned with our peer groups, we felt like it was important to put 2 kind of intermediate stakes. And it was a hypothesis that those would be energy intermediate stakes. And so we have 2 plant options that aren't that far stake in the ground. This is the first one. And this is actually modeled after that Legacy Salmon Creek example that we looked at for our energy monitoring. So it's essentially a distributed heat generation plant. So the boilers, the steam generators are generating the heat at the level it needs to be. So not everything's steam all the way up to a really high level and things being dropped down. It's a point of use type system. And then again, a pretty traditional chiller that's not connected to the heating system. The high performance plant 3, so the middle option is the central concept is a heat recovery chiller. So the boiler and the chiller are combined in function. They're connected when there's need for heat or cool, if it's able to do that in a connected way. This is another important point, I think, is that when there's a choice of like, do we include it or do we not, it's kind of on the borderline. So for example, a supplemental boiler, do we really need it? We put it in because we wanted to err on the side of being conservative. Another example is radiant heating panels at the sidewall in Phoenix and LA. Maybe you don't need it. Maybe a week, a year you do. So we put it in for the cost model, so it's represented there. So in this case, the heat recovery chiller plant has a small supplemental boiler, a small supplemental chiller when the heat recovery chiller isn't enough, and then again, a cooling tower. And then the final, the far stake in the ground was this ground source heat pump plant. So essentially the ground working like a battery. The heat can be stored when you don't need it or extracted when you do. And the heat doesn't always have to go into the ground. It can loop through the heat pumps at the plant. And then, again, a supplemental chiller. And I believe the sizing, we had a change in the sizing. Initially, the sizing of the bore field was for the entire load, including the peaks. And now we're sizing the bore field for the base load and then using peaking chiller and boiler. So that's changed a little bit. So here are some results. I should mention that we're probably at about 90% completion on the energy models and about 75 on the cost models. So you're seeing late-breaking results, but not final results here. The final results will be at the end of the year. But I think conceptually, they work. So what we're seeing here, and again, this is New York data, is that annual loads graph again. So January to December, the load on this axis. The blue is the cooling load, and the red is the heating load. So the heating, if you were to be more high performance, you'd be closer to 0. On the cooling, you'd go down, closer to 0. So you can see the curve of the graph. You can see the peaks are up here and down here. And what we're trying to do is reduce those peaks and reduce the area under the curve. This is actually a direct snapshot from the tool that we're generating. I'll talk about it a little bit more later, but you'll get a flavor of what the data looks like. And essentially, you can compare the different cities across the right and click on those and make them bigger in the tool and dive deeper. For example, looking at the high performance options. So on the top again is the cooling load. On the bottom is the heating load for the high performance. And here they are overlaid, so you can see the difference. You can see that both the peaks and the annual energy use are reduced. And one thing that our mechanical engineer likes to point out, which I think is pretty interesting also, is that this almost looks like a mistake on the high performance heating load. It looks like it's a repeated data in the graph. But really what it is it's the turn down at night. So for example, the ORs and the kitchen and the ED, when they're not in use, they're scheduled to be turned way down. They're still an overhead mixing VAV system, but they turn way down at night, and you can see the implication on the heating energy for that turn down. Quickly, so these are the peak hour of the peak day, looking at here heating, and you can see where different things are reduced in that peak. Here, a lot of overcooling, so the reheat is reduced on the heating side, but everything is pretty dramatically reduced too. And what this means is smaller equipment, so smaller chillers, smaller boilers, et cetera. And then cooling also. We've separated it by latent and sensible to see the reduction there. And do you want to say anything else about
one
that?
of the things that when you see these peak load reductions, we've seen this in other building types. We've worked a lot with the Northwest Energy Efficiency and other building types, schools, retail, grocery stores. And our experience over the last 15 years has been, there's a lot of waste going on here. And if we can start to pull out what's wasting energy, there's usually systems that go along with that. And then we can take that cash and sort of store it over here, and then we can spend it on the things that are going to allow us to be more high performance, let's say a heat recovery system. In retail, in grocery stores, it turned out that grocery stores had the same problem with reheat because they tended to have great big cooled chiller boxes for all their frozen foods. And it turned out that you were basically walking into half of a store that's a walk-in cooler. You don't know it, there's no door there, but there's a massive heating system going on right over your head, just pushing hot air down into those cooler decks. So in the summertime, so they don't form little rain clouds. And they burn gas for the heating, and they burn electricity for the cooling, all simultaneously. And what we worked with several large grocery store chains is to recover heat off the chillers and use that as their heating system. So all of a sudden they could pull out about 80% of their heating system. And that's money savings. And that's exactly what's going on here. When we can reduce peak, we're saving money in systems, and we're going to reinvest that somewhere else, which Heather will talk about, like right now, I think, or something.
Well,
Close.
one more
Close.
thing before that. So this is an example of the solar load. So we talked about the exterior dynamic shading, and here we can see what kind of effect that has. This is the west zone. So it's actually marked incorrectly on this plan, but this is the plan of scheme A, and it would be the west zone of that plan. And we can see the orange is baseline, blue is high performance. So you can see the reduction in the peak solar load in that zone over the year. So over the year, it's cropping it down. And if we look at the peak day, this is what it looks like. So this huge peak in the afternoon, that makes sense in the west. And we just lop that off. And why that's important is because the chilled ceiling panels, radiant chilled panels, can't accommodate that kind of peak load. And so we need to lop that off, and not to mention the displacement ventilation wouldn't work.
As all mechanical engineers would tell you, and the facility operators, there's a horrible sort of chasing your tail thing going on here. When you have chilled water at roughly the same temperature all the time, you can't chill it more as it gets hotter during the day. What you have to do is you have to up the fan horsepower. You have to increase the amount of ventilation air going through. It's not unusual for us to see 12 air changes in a patient room in the afternoon on west facing, just be able to get enough cool in there to make it work. Well, when you increase the fan horsepower, you're putting more heat into that ductwork because it's all part of the same system. So you cool more, you cool more, you cool more, you have more load, and it's a really bad cycle to get into. And this is one way of breaking out of that.
Yeah, and not to mention what the other facades look like at that same hour, right? And getting the same supplier. So here's the energy results. So this is the annual EUI results. It's a lot of data to digest. So I'm going to point out New York. I'm just going to point out the overall picture here, and then I'm going to dive into New York. But essentially, at this 80% draft, did I say 80 or 90% draft, we are able to achieve the target 100 in all but 2 of our cities. The 2 are the cooling-dominated climates, Houston and Phoenix. I think it might be LA. And we're really close in those. So the percent reduction, as Joel mentioned, we're looking at that a little bit less. You can see, well, I'll just go to the next slide to show New York. This is the database baseline. So if you go to Target Finder, you put in a hospital of this size, you'll get a Target Finder result of 222 kB2 per square foot year. You can see the bar next to it. That's our code baseline for Scheme A, which is even higher than what the database shows. So we're a little skeptical of that number. And so a 60% reduction from that is, we think, an artificially low starting point. But we still get to 55%. So we're close, and we're hitting the targeting 100 goal in New York. Another thing to point out here is the relative similarity between Scheme A and Scheme B in the energy results. There's a modest difference here, but essentially we chalk that up to that they're really internally load-dominated buildings, and so there isn't a big energy difference. The good news is having a more articulated envelope is not an energy penalty, which you might think, because there's more envelope, potentially more heat loss or heat gain, but it actually works well. And then as we move beyond targeting 100, say targeting 50 or targeting 0, this more articulated form gives us more resilience to be able to do that. There's more options on the daylighting side. There's potential for natural ventilation. We're also, what that implies is you can see this stacked bar chart. The big piece now, we were talking about the big target of opportunity here is reheat, which is the red piece, which is drastically reduced. The big target of opportunity here is on the electric side. It's the plug loads, which is something that we need to understand better. First, how much do different pieces of equipment use, and then how do we reduce it? So to me, that's the next big puzzle to figure out if we're going to move beyond this targeting 100 goal.
So one of the things that you can see those 2 intermediate options, option 2 and option 3, for both schemes, where the greatly driven by facility managers and building operators, owners who said, I can't do the ground source heat pump. Just can't go there, And we showed a lot of options for doing this, even in urban settings. The Bullitt Center, which is an urban building, we have 26 400-foot wells underneath the building. And all the manifolds are accessible. Everything works, but it made them very nervous. So we have these basically VAV options that are heavily VAV and plant systems that are very traditional. So, but what really surprised us was, and thank you owners, is that option 3, really, option 2 and 3 performed really pretty well. We were surprised that, we couldn't quite hit 60%, but we could hit 50%. And so we all felt a little embarrassed, like, oh gosh. But on the other hand, our line is exactly what Heather said, is that if you are thinking about going to 50, which we need to think about, you'll never get there with traditional plant systems. It's not possible. So we need a really high performance plant system. This gives us a sense. Those traditional plant systems with heat recovery chillers, you will see in a second, are expensive when they're running this high up performance. So you think, oh gee, that's not so expensive. It's the same traditional plant that we're sort of using today. We're using a lot of heat recovery chillers. But it turns out that it's a little bit cheaper, but not that much cheaper. So we're getting a lot of performance, but it's costing us a lot. Not quite as much as the ground source heat pump, but.
Yeah, I'll add a couple of things to that, and that is that these options are the displacement ventilation with radiant heating and cooling systems, but they only vary at the plant level. And another interesting result, and I'll show this in the next slide, is this distributed heat generation plant and the heat recovery chiller are more gas dominated. So when you're looking at the energy savings, option 4 is the most energy saving option. If you're looking at energy cost savings, it's a different result, because the cost of electricity, we'll just go to it, in New York is really expensive, and you guys know that. So having more gas is ultimately less expensive. So if you're looking at LEED, for example, you would be looking at energy costs, not pure energy reduction. So here's New York. We see the baseline. There's a 30% reduction in energy cost for the distributed heating plant, 30% for the heat recovery chiller plant, and 31% for the ground source heat pump plant. I don't think I read that quite right. But in any case, you can see how close the results are, but the cost of electricity in these two are way more. So it just is a decision-making process, and that's, I think, an advantage of having those 4 plants and be able to compare them and having a suite of options to look at.
We also were pushed for a while into looking at cogen. Gas is so cheap, electricity is so expensive, it makes a lot of sense. And we think of this as an intermediate technology. Our position related to it is that a BTU is a BTU, and they all levelize over time. And if we spend a lot of money, because natural gas is extremely inexpensive right now, we know that over the 5-10-year cycle, that if it's really cheap, everyone's going to switch to it, and the price is going to come up. So we were very skeptical of that. But there are places for right now where it makes a lot of sense. 2 of them that make the most sense: New York, probably Boston, and Houston, of all places, because gas is so phenomenally cheap in Texas.
I think the other part of that is that we fundamentally, as a team, wanted to look at load reduction first and then efficient plants to apply to that. And one could choose, we didn't test it or cost it, but one could look at cogen once you've done the load reduction strategies and see how much that, how that works in that project.
To really quickly say, cogen is the use of natural gas to turn gas turbines and make electricity. So you can use the heat out of that process, and you can generate electricity. So it's an interesting little plant. It's used in the Dell Children's Hospital. You go to Dell Children's, and here's the hospital, and you go across a little driveway, and here's this big walled-in brick thing that turns out is quite a large power plant. So there's a question back here. Yeah.
No, I think that's a really good question. Yeah. Well, and it depends on your region. Like in Seattle, our electricity is green because it's from hydro. A lot of it's from hydropower, and that's our goal to show that in the final tool. I have not run the numbers, but it depends region to region for sure.
Another issue is if you're ultimately worried about greenhouse emissions, you've got to move to electricity. You cannot be burning stuff on site. I mean, we'll look at this as archaic, that we're like have fires burning in our buildings. So how do we get there is the question. And we're in a change, and there are going to be a lot of ways to navigate that change. And that's a really great metric that we're all concerned about.
So now cost. You're not meant to really read this table. I just put it up here so that I could talk about the cost models. Our energy models are very detailed, as are our cost models. I'm not going to show the detail of them here, but they're like a 200-page report where every piece of equipment went out for a quote for every city, and so each line item was looked at city by city. It's in a standard uniform format summary. So essentially, this is Chicago. This is actually Houston data. Sorry, I thought this was Chicago data, but in any case.
The story's about the same anywhere you go.
The story's about the same, and I'll show kind of the general story. And as I said, this is at a 75% draft, so don't put too much weight in these numbers, but we think conceptually it's really close on the percentage differences. But we think it's really important to get the cost per square foot total for the building and per line item really close to what market is in each of these cities, so it's close to reality. Essentially, what this says at the bottom line is and I'll show a summary graph of this in a second, the cost, there's an incremental cost of about 2% for the plant 2, about the same for the plant 3, which is the heat recovery chiller, and about 5 for the ground coupled heat pump plant. That 5 is based on the bore field being sized to the peak, not to the base load. So that'll change with our next draft. And they're definitely, this is meant to represent their cost adds and cost deducts in different areas. This is just looking at the mechanical systems as an example, and the color scheme's a little different here, and it's a little hard to read. So the blue is the baseline. So for example, in dry side distribution, the baseline is more expensive for dry side distribution than the high performance options. That makes sense. We're distributing less air in the high performance options. We're distributing heat and cool through water, so pipes, not dry side distribution. So the wet side distribution, on the other hand, is a lot lower on the baseline and a lot higher on the high performance options. So these cost adds and deducts make sense. But the important point is that the overall result of the incremental cost is very small. This is at a schematic level of detail, the design, and there's a lot of cost shifting that happens. It also requires looking at the budget probably pretty different than a traditional project where there aren't silos for different categories, that they're shifting between different categories. So for example, a cost savings in the mechanical system might shift to the envelope in the architectural systems to help, because the architectural systems are part of the cooling system at this point. So it's all one budget. This is showing those incremental costs overall, and you can see the cost per square foot. The New York data was not complete at the time that we put this presentation together.
I should say the greatest amount of skepticism right now for those cost numbers come from architects. And being an architect, I'm a little suspicious that we're really locked into these silos of costing, and that they see an increased cost of mechanical, and they say, well, we just can't do this. And what we're saying is, there's this flow between architectural, mechanical, and electrical that has got to occur. And so a whole new omelet is being put together here, and your old cost silos just do not work. And it's going to cause some ripples and some hard times, but it can work, and we've seen it work in Seattle. Yeah.
More effective, you're the ones that get stuff explaining to the owner who wants to, as they see this, oh, the envelope is this.
Could be, especially if you have, the owner has a cost consultant who's working on sort of standard performa CSI division format, costing. And so our best experiences in that come from bringing the owner and whatever consultants they have, Hamas or whoever it might be, into the team immediately in the beginning and explaining this, and where everything is out in the open, and there's a commitment for everyone to plan it, design it, construct it, and operate it within the parameters that are established initially. And it works pretty well most of the time.
So here's the summary slides that I mentioned that I'd show. So looking at scheme A versus B, looking at the same plant between the two, there's about a 6% cost add for scheme B. That makes sense. There's a lot more envelope. For example, the exterior dynamic shades, there's twice as many of them, twice as many windows. So we think that's an important difference. One of the things that the study does not quantify is the difference of what it's like to work in scheme A versus scheme B or HEAL, the more qualitative aspects of what scheme B might bring as a benefit to the healthcare organization, to the patient environment, which we think are really valuable. And that 6% might look like nothing compared to being able to retain a nurse or not retrain another nurse.
So we certainly haven't looked at total cost of operation. I think that's where if we could look at total cost of operation for over a 30-year period, and we could attribute those savings in, let's say, retention of staff or healing performance, that 6% would evaporate. You're just not concerned in TCO with capital costs nearly as much.
There are some, not huge studies, but some studies.
Oh, yeah.
Determine length of stay.
Yeah.
Right.
Absolutely. I hope that there's some connection. It's the way that this is structured is it's so quantitative and there are numerical answers. And the way that to connect those studies to this, it's going to be a more qualitative discussion. And that'll be part of this. But we're not going to quantitate the total cost of operation.
So if we can
those
make it work
studies.
without bringing those attributes in, that's great. On the other hand, we think there needs to be more evidence.
Yeah.
You know, we know that those things are true, just in our heart, in our gut. But others don't, and really challenge that evidence of increased healing, decreased pain medication, increased health of
yeah.
people who spend more time in daylight, especially for shift workers. You know, there's a great study, the Boston, that huge nurses study, which looks at shift workers and the prevalence of various maladies, breast cancer and things in shift workers versus non-shift workers. All of this is part of that sea change that we're talking about.
Yeah. And I think we're looking for a more quantitative connection between those two things, as I think we all are, because we do feel like these attributes are so important. But to be able to sail them, they need to have grounding for depending on who's the decision maker.
Excuse me, there's another
Yeah.
factor. Having done a number of scheme Bs in the UK, having done many scheme As in the United States,
Yes.
it's much easier to get your adjacencies to scheme A.
Yes.
Your functional flows
Yeah.
work in scheme A than wrapping around corners and operating on suites in scheme B.
So the comment is, it's a lot easier to do the sort of internal functional planning in a long span concrete space without windows, because you can get the adjacencies very quickly. So they're more efficient for those things. And there's no question about that. But the question is, how healthy is it for all the people working there?
Mm-hmm.
I don't know. It's an interesting question, which we'll all debate.
Yeah.
Beyond my careers.
And that's another reason why we felt it was so important to be able to look at the program and have the same program and make sure it worked in Scheme B. And it's interesting that Duncan Griffin, who we worked with at MBBJ, felt like the efficiencies in Scheme B were actually better in this case. I'm not a medical planner, so I'll let him, speak to that. But in any case, it probably depends who you talk to.
Well, that actually relates to something we're going to suggest that comes out of this in a few minutes. It's sort of the end about this debate.
So the difference between the baseline and high performance options. So in both Scheme A and B, the relative percent differences are about the same. So for to go from the baseline to the farthest stake in the ground, the ground source heat pump plant's about 5% cost add. The middle two plants are about 3%, about the same to each other. And what this does not incorporate is potential utility incentives that might come out of this kind of whole building energy efficiency evaluation. And it's also, as I mentioned, at a schematic level of design. So we think that in the Pacific Northwest, if one were to design this kind of building, which Swedish Isokol will show at the end has, it's about a 1% incentive from the utilities. And actually, I think they got a bit more than that. That was a conservative
It's
estimate.
the largest utility incentive Puget Sound Energy, big utility like Ingrid, had ever provided. And it was a little more than 1% of the total cost of construction.
So essentially what we just talked about. Oh, yeah. Question?
Well, I just wonder, just if you go back to that slide, if you compare Plan A with Plan B, Scheme A with Scheme B,
Yeah.
which is a 6% increment, and then you get
5%.
Plan 1 and Plan 4,
Yeah.
which is 5%, those are not strictly additive.
So if you were to compare Scheme A baseline to Scheme B4,
Yeah.
it would be the 6% plus the 5%.
It generally is pretty additive. I mean, there's
Yeah.
a little bit of fussing around, but
Yeah.
in a
It-
big picture,
I think one of the things you might be also asking about is that the distribution systems are different between the two. So the Scheme B is a little different, and that'll bear out in the details as we get each city. It's different city to city.
And the plan is only about sort of, what, 35% of the total cost anyway, so it's maybe a third of 5%.
right.
Right, right, yeah. So what we just talked about, and I think I'll have a couple more slides after this, is that integrated design is really important, a key to success here. And it's both about the team and the systems integrating as a whole. Load reduction is really important to the fundamental philosophy of this project. And these systems have been used before, maybe not in healthcare, maybe not in our experience in healthcare, but they're not unique systems. And doing these things, you can get that 60% or targeting 100 with very little incremental cost, and common payback in less than 5 years usually. We want to mention that targeting 100 is one kind of roadmap. The Advanced Energy Design Guide that ASHRAE put out earlier this year is a great resource as well, and we collaborated really closely with that team to make sure our energy models were in coherence with each other, sync our baselines to make sure we're close to one another, and they present some different strategies at the building mechanical level that are also, the path to decoupling the heating and cooling from the ventilation air. For example, using distributed fan coil units, distributed heat pumps. We chose one strategy, and so you can look to this document to find other strategies, kind of performance-based goals. We just decided to cost, one building mechanical system.
The costing of all those systems was just impossible for us. But it's a great periodical. You ought to do it. You ought to get it. If you don't have it already, it's downloadable for free from ASHRAE.
Yep. A couple of things that set this targeting 100 apart from the ASHRAE 50% AEDG are that we're creating a tool to disseminate this information. Essentially, it's a website. And so you'll be able to find all this information at your fingertips online. Our goal was we wanted it to be on a handheld device that you can carry around, access the information from wherever you are, and targeting several different groups of people. So Ben actually helped us out with this in New York, thinking about kind of really high-level introduction for people that have 2 to 5 minutes to look at this, kind of a mid-level where if that person decides, this is interesting, someone else could look at it. So an introduction for architects, mechanical engineers, partners at a firm.
20 minutes.
A little deeper dive. And then for the people that are charged with implementing this, we have information for them too, and it's at a deeper dive level. For example, the 200-page costing report will be at your fingertips if you want to look at it, and you can download it and help us know if we made some mistakes in it. There's always room for
Outputs
growth.
of all the energy models, very
Yeah.
detailed outputs, all that.
So, and I just wanted to mention here, you see this 4%. This has been in development, and the report that the energy use of healthcare in the U.S. went up by 1% happened since we put that slide together. So that's kind of interesting. It's ever-evolving information.
So we've been working with lots of people from all across the country. It's really exciting, great people, giving us lots of great information. As Heather said, we're really interested in the research, but we're more interested in actually getting one of these things built, you know. And we've been working with design teams in the Northwest and in California related to this. So we really urge you to think about how you can utilize us as those resources. This is a list of projects that we've worked on. These are just healthcare projects, which we're obviously here to talk about today. You can see how the EUIs have sort of dropped over time. Now, some of these are medical office buildings. Here's the Children's Medical Center medical office building. This actually has 6 surgery suites on the 2nd floor, and it's a clinic on the 1st floor. So for it to break 100 is an EUI is important, but it's not just, you know, it's a hospital without beds is what it is. And those darn beds, those units use a lot of energy. But this hospital, Swedish Issaquah, is a project that we've been working all across NIA for about 10 years through the master planning with the developers and with the hospital owners, and then through design and construction, working with them to understand what goals are, how you can meet those goals, and then persistence of those goals through operations. They weren't capable of doing our sort of ground source heat pump, and they didn't want to decouple because NIH hadn't accepted this displacement ventilation system. But they have an operational EUI sub 130 right now with a fairly traditional hospital, brand new greenfield hospital with an average, it's almost exactly the same as our hospital. So we're really proud of that. We think that it probably is one of the most energy efficient hospitals when you dig into the details and where the heat comes from in the United States. And as I mentioned earlier, it's on the cover of the AEDG. But this is what we really should be thinking about, and has been our dedicated process over the last 10 years, is to bring new information to the architects and engineers in the Pacific Northwest and challenge them with that. And they've been really up to the challenge, we think. We went to health design in 2004 or 5 and heard the initial presentations of Karolinska, where white architecture presented it and described it as having an equivalent of 50 kBtu per square foot year. And this is with renewables, but not a phenomenal amount of renewables. This is load reduction. This is a big research hospital in Stockholm. So this was shocking. You know, we were trying to figure out what the problem was, and we found the average was about 250 in Seattle, and they were talking 50, and we were crazed by that. So Heather was a graduate student at that time, so we found a foundation to support her to go off to Scandinavia and to do analysis, which continues to today. We were just looking at some data from these hospitals that we've been looking at. How could this be true? She put this chart together. I think maybe you've probably seen it presented by other people, but the average of existing Pacific Northwest hospitals is up here in this top bar, and EUI is on the horizontal axis. Here, this was 263. This is what we thought of as sort of energy code, and here's the 2030 challenge at 100. Here were the hospitals that Heather looked at in Norway. Operational hospitals. Some of them are more than 10 years old, and they're operating. These are big hospitals. Riks Hospitalet, which certainly is a great urban experience. Won the RIBA Urban Building Award, I think, in 2008 or something like that. Operating at 117. Okay, so these hospitals are operating basically what our goals are, and they're not crazy. So Heather found out this information, and then we decided, you know, we need to put together a tour. So we took about 25 people from Seattle, hospital owners, C-suite folks, architectural partners, project managers, engineers, big general contractors, Mortenson, City of Seattle, and we took them all over there and said, look, we've combed all through this stuff. We want you to look at it, and we want you to figure out, you know, what we're not seeing. And the primary thing that came back from that is you know what? They're really not doing anything differently than we could do. They're not using any sort of miracle system. They're just doing everything better. You know, their healthcare regulations, although they're not countrywide like ours are hospital by hospital, and they're very comparable to what ours are. Now, patients are a little different mix because their healthcare delivery system is a little different. Maybe they're a little less acute, but that shouldn't make this huge difference that we're talking about. So this work that Heather did, and especially with the Swedish work, which you see the Norwegians, who are considered to be sort of the Texans of Scandinavia. You know, they have all that oil and all that energy. You know, they're driving these big cars and loving it. And look at the Swedes down here. This is at 50. Here's operationally Karolinska existing. This is an old hospital at 94. The existing average of hospitals in Scandinavia, it's 70. So this is huge information.
I think I'll add a little bit to that graph. An outgrowth of that tour, and Joel will talk about some of the strategies that led to targeting 100 and why we chose what we did. But right now, we were looking at some slides earlier today. I'm working on a project to run those numbers through Portfolio Manager so that we can have a comparison that we understand and make sure that it's apples to apples. There's some differences, and we'll see. It remains to be seen what the result of that will be, but it's a comparison of Pacific Northwest hospitals, the climate's similar in the Pacific Northwest to Scandinavian hospitals through a system and validated system that we understand.
So let's look really quickly in the last 5 minutes here of some of the things that we found. Here we see reeks here. This is also reeks. I guess this is reeks all through here. Natural ventilation occurring in big public spaces. So these are radiant floor systems and naturally ventilated whenever they can. And beautifully daylit, as you obviously can tell. Displacement ventilation systems. In 2007 or 8, we were there prior to taking people over. And we walked into this patient room, and we were looking at it, and we realized the ceiling was a hard ceiling. And we were thinking, where in the heck is the air coming from in here? And then we found this. And whoops, this in the corner. This is displacement ventilation. This is supply air, return air. And we're like, does anybody, we haven't seen a paper, anything written about this. It's been operational for 3 years. So it's interesting what you bump into. Deep bore, really large ground source heat pumps are the norm. And I think it's something that we can look towards. This happens to be a pretty green, this is Akershus outside of Oslo, and has a pretty greenfield site for a ground source heat pump. But Karolinska equally has 400 to 600 foot deep bores in a very, very urban site. Might as well be built in downtown Boston. Exterior operable shades and operable windows. It's an interesting question. When we talk to the Department of Health in Seattle, and he actually talked to Ashpad in California, they don't rule out the possibility of operable windows. In fact, Ashpad used to require operable windows, and you had to present a petition to not have operable windows in your healthcare environment. So we think those are interesting things that we can begin to look towards. Here are the operable shades on the exterior of big new hospitals. This is a sunny day on the south side. You can see that they're manual overrides. You got to realize when you manually override to open that window up and you have a cooling system that can't accommodate it, that there will be sort of a human switch that will say, we need to put down those blinds. But if you really want to have them up for a period of time, in some various, you can do that. On the other hand, here's an overcast day and everything's wide open. The amount of time, now we're looking at the amount of time that these shades are open and closed in the energy models. Is pretty interesting to see that they're generally open and closed 20 to 30%.
Yeah,
right? Closed 20,
early
30.
to say.
Yeah.
Yeah.
And centralized district heating and cooling systems and waste to heat systems. This is happening at St. Olaf's, this little photograph here. And they have the most amazing trash cycling into furnaces which burn this waste and then clean the air that comes out, the exhaust that comes out of this to an extreme extent.
They have big robotic distribution systems, including from the clean side up to the patient rooms, and also from the waste sorted out. So garbage, linen, something else are sorted.
So when you're walking around down in the mechanical shafts and the service shafts below the building, you see these giant tubes, and they're all running overhead. And about every 5 minutes or so, all of a sudden you'll hear this thing go whoosh down one of these tubes, and it's a great big sort of 40-pound bag of something that's coming from somewhere, going down that tube to this district heating plant. So key concepts for Karolinska and for all these high-performance hospitals are really reformulating the building envelope to make them healthier places to be. An extreme amount of daylight, huge amount of window area and skylight area. These are actually, in Karolinska, skylights done into a retail floor, retail levels, and in places, skylights that go down into the kitchens, because you'd never build a kitchen without daylight. Isn't that amazing? And reformulating the HVAC systems along the lines that we've talked about. Again, these are the projects that generally we have worked on as a technical assistance process and really trying to find out how this rubber hits the road. Our best experiences have been probably not only hired by architects, but hired by owners to do this. So to help them set those initial goals in master planning and work with the design team in carrying the energy model through with their mechanical engineers, so that the early master planning energy models coincide with the construction documents and operational directions to the owners to how to operate the building. So we end up with an energy model that's calibrated to operations in the end. So the way this is going to happen, and that's the most important thing, is through something that we're projecting as Healthcare 21. And Healthcare 21 is just like Labs 21, in that lab buildings 10 years ago had a problem with energy use. And it really didn't get solved until people started talking together about the solutions that they were finding, owners, operators, designers, contractors. And we think the same thing is true here. So it comes back to this question of exchanging information, finding out what works and what doesn't work. And we think that this at a regional level is really important, and that we are proposing to the US DOE and EPA to be able to begin to support the idea of regional groups getting together around performance issues, dominantly energy, in healthcare over the next 2 years. We think it'll culminate, hopefully, in a national meeting, maybe once a year, maybe coincident with Clean Med, that can do this very same things at a national level. So watch for that. So you can also get an overview of this graphically through a poster that Heather put together with several of our graduate students, which provide a summary of this. You can download this from our website at idlseattle.com, and all the other information that we have under health design. And we want to thank you very much. I think we're 5 minutes over.
Thank you very much.
Sure.
Sure. So the question was regional differences, and it doesn't look like there's a lot. And we ended up, in the end, we thought we did a pretty extensive climate analysis. That'll be a part of the tool. The climates are quite different. Ultimately, the solutions are pretty similar, climate to climate, and we think that's because of the internal load-dominated problem that's happening in healthcare. There are some regional differences that are more at the subtle level. For example, the envelope, we think, needs to be more robust in the northern climate zone regions. Humidity control is a big one. We initially, in the southern climate regions, had incorporated dehumidification into the building mechanical systems, and in Seattle, for example, we did not, and in Phoenix, we did not. But ultimately, we decided we should, because there is humidity problems everywhere. It's just a matter of degree. So do you want to add to that?
There's one thing that comes up, and that is, we think, and we didn't have time for this, but if you start to push the envelope a little further to R25, I think we're at R20 right now, and it's basically a 1-inch foam wrap on the building. But if you push about to R25, that you can eliminate heating. With the given miscellaneous loads that we have inside, heat recovery will be able to carry the heating in all but really unusual circumstances. And pulling the heating out and just the piping for that is so, you might start to think about in these northern climates, because they're the ones with a little more heating, to insulate the envelope a little bit better. You might even think about going to triple glazing and being able to pull the heating side out, at least the perimeter heating, which would be pretty interesting. That's pretty much what's happened in the Bullet Foundation building.
So I know we have really quick are you looking at any adverse requirements actually change the code?
Are we looking at code changes that should happen? So it needs to be emphasized, we didn't do anything in these models that doesn't fit the code. Yeah, I know. I just wanted to reinforce that because it comes up a lot. There are things that we've looked at in terms of ventilation. Ventilation is hugely the energy problem in hospitals, and it's less driven by knowledge than by tradition. So, and we found that in lab buildings, right? So we need to really push on that, and then we also need to really push on the equipment that goes in those buildings. But all those things outside of ventilation are non-regulated. Heather, do you want to add to that?
Yeah, I think how I'd approach it is that we can hit targeting 100 under this code that we have today. To get beyond that, we need to look at ventilation rates and understand and be able to open the windows and use natural ventilation and understand how much connected load for lighting versus how much lighting is actually used. And I think there's a lot of room for growth there. It's not part of what we're going to present by the end of the year, though.
The expanded comfort zone, which was really developed for office buildings, ASHRAE 55, and we sort of talk about it like, oh yeah, it can be used in healthcare, but we don't really know that. But in Scandinavia, what you find is there are operable windows and operable doors in patient, and people can walk outside. Oh my God, from their room, and what we think based on the 55 standard is that gives people a less claustrophobic sense of temperature control. So they allow the temperature to rise to 80, 82, 84 degrees in their patient rooms. And at that level, they can produce enough cooling in the building through the ventilation air that they don't have to put separate cooling systems in. So if we would have research that would begin to indicate that patients would be, if given this operability, would be equally responsive to an expanded comfort zone, then it opens all sorts of doors if we could get the infection control folks to go along with, the flora and fauna that come along with operable windows.
Just to add to that, my reading is that the hospital-acquired infections in Scandinavia are no higher than they are here.
Yeah.
I believe ASHRAE 170 actually did lower that a couple of years ago, for patient rooms, corridors, and miscellaneous rooms. It dropped it 20-30%. Based on prior 170. But I do have a question for the board. Did they consider it thermal mass at all? The differences on buildings with thermal mass, higher and lower, wings and...
We didn't, and it's just a more complex model than we wanted to get into, but it's certainly an issue. Heavy buildings are more resilient than lightweight buildings, and our buildings have become more and more lightweight. So, but it's a good question.
I think I'd return 1 second. I'd ask Hubert or Ben or Carlos or David, what examples or similar examples have you seen regionally here in New England of similar systems or buildings taking a similar approach to what Heather and Joel have talked about today?
Maybe I can just start off. Since I work with Partners Healthcare, let me sort of boast about our 2 recent buildings. The London building, which has 28 operating rooms and something like 130 beds, is now tracking at 168 kBTUs per square foot per year. And that's the most energy intensive building I think we have in the entire system. The Spalding Rehab Hospital, which does not have operating rooms, is tracking, and I stand to be corrected by folks in the audience here, I think it's at 146 kBTUs per square foot per year or thereabouts, which is, sort of not bad. What I wanted to do to sort of substantiate what Joel is saying is that on the Spalding, we managed to actually get rid of the perimeter heating by adopting triple glazing in the patient rooms. We have natural ventilation in the public spaces and in the gym and the pool, the therapy areas. And we have operable windows in emergency circumstances. That was the sort of compromised position throughout the building. And that was learning from Hurricane Katrina.
I'm Carlos Alonso Niemeyer with NSTAR, and I'm just very proud to tell you that in Massachusetts we are really leading the nation, actually, in energy efficiency. All of the things that we do are based on code, and as you know, we have the Green Communities Act, which is now requiring that every building that is built, it's about 20% more efficient than just the regular code. Our incentives, the ones that we have to offer everybody, are based on people beating the code. And we have done pretty well. We are seeing some shifting. Actually, right before I came here, I just checked with the people that are doing some of these projects for confidentiality. I'll tell you, but yes, we're seeing a lot of shifting away from the BA boxes, actually, and work being done to basically disable or change or make some other changes in that sense. The other thing that I wanted to point out is that you mentioned the 1% increase on the cost, and that's pretty much on the mark. We have seen that on large construction, it's about 2% to go from a base case building to an energy efficient building. And the way our program works, we can pay up to 50% of that incremental cost on retrofit and up to 75% on new construction. On very large buildings that have a lot of, that are very energy intensive, we can go up to 90%. And usually that only happens on labs or hospitals as well too. So that's pretty much on the point. One of the comments that I will have for the numbers that you had, the cost of energy in this area is the highest. So when I see Houston and Denver, 5 cents a kilowatt, then it's gonna go nowhere. Here, our clients, hospital owners, are really looking at the bottom line. So targeting 100 is not just trying to save the earth and sing kumbaya. It's basically hurting their pockets. So we have a very aggressive program. And I just wanted to let you know that yesterday it was announced that Massachusetts, second year in a row, it's the #1 state in energy efficiency. So it's all because of you as well.
Can I just ask what the price of energy is in Norway and Sweden compared to us? Yeah. I mean, that must be an incentive.
Let's get that cord over there. This is crazy.
Yeah, the question was the price of energy in those Scandinavian countries, and it's significantly different than here. The price of energy is actually pretty similar, but there's heavy taxes on it. So the fluctuation that we see in energy prices is just mellowed out by the amount of tax that's put on it. So there's a lot of incentive to save energy based on the payback.
So as a follow-on to that, how do you see New England as being different from the rest of the country or differently motivated to put energy savings into our country?
One more comment from the first question, David Belva from Air Acuity. We're actually seeing a lot of laboratory-oriented projects go with chill beams to decouple the ventilation load from the sensible loads, and that's really resulted in some significant energy savings because, as we know, it's a lot more efficient to move water than air through buildings. So we're seeing a lot of this in the laboratory research space, but to be honest, I haven't seen it quite yet as far as healthcare goes. And my question back to the group, really to Joel, it would be, this sounds like a tremendous opportunity, just from the standpoint of the energy savings and the small incremental costs. So to me, the payback would seem realistic. So the questions back when we get to it would be really, what are the hurdles you're seeing of this being really adopted by really healthcare professionals and decision makers who have to write the checks to build these hospitals? Because to me, it sounds very good. You know, I would sign up in a minute, and it just seems like there must be some other challenges you're seeing. So maybe I'll defer that question to after, and we'll go back to your previous question. If you could repeat it.
Do you see New England as being fundamentally different or differently motivated than anywhere else in the country?
At least us from the utilities, you know, we are eager to make sure that people are saving energy because we have to save energy. That's part of our mandate. But yes, we're seeing it ourselves, and we talk to other states. We do have the funding that makes a big difference. Actually, states like Connecticut, sometimes they, or New Hampshire, where the programs run out of funds. That creates for problems also in the long term. These buildings have a 2-year turnaround just on the design. So you can't be thinking of incentives and energy savings expecting for the money to be gone in 2 years. So for us, one of the successes of the program is that the funds are secured and are going nowhere. And we are seeing those changes. Actually, there's a couple of major hospitals going on right now where, as you mentioned, it's very important to have all the players at the beginning to understand. The other thing, too, that is critical is you mentioned that when designs are being made, you have to adjust for changes on the load and the equipment. And for us, our incentives are based on that as well, too. The biggest thing that we can do is to help pay for glazing or daylight shades if we're going to be able to reduce the chiller size, etc. And our incentives are based on those changes. So it's critical to have this whole comprehensive design process.
Or as a follow-on to that, I think the analysis to do during the design phase, it's not simply doing analysis after the fact of this is what we're actually constructing, but to look at those, to have incentives that support the whole building energy modeling that you can do during the design phase to find that sweet spot. Which some of this research has shown that, yes, getting to 60% might have that 2% or 5% cost premium, but that 40-50% energy savings is readily achievable right now. And we have to factor in the support and the numbers and the metrics early on to be able to support those design decisions to end up through the schematic design VE process. And that's when the incentive programs come in that push us to do the early analysis. And also integrating with design teams of saying, let's look at the facade, let's look at the systems, how do they interact together?
It's interesting that he mentioned the incentives. The reason why we don't call them rebates, it's because it's an incentive. If people were doing their energy efficiency measures without our money, the state sees it as they were going to do it anyways, so why give the money? So we have to demonstrate that we were able to incentivize and really change their thinking. So for us, it's critical to be at the beginning, especially on those energy modeling sites. We actually have, for larger projects, we have a way of cooperating with the cost of energy modeling because we see it as an important tool. And we very much pay up to 50% of that cost for these large projects because we believe it's a fantastic tool.
Maybe as a follow-on, and this may follow up with some of your questions from the audience, what are some of the biggest obstacles that we face right now in implementing any or some or all of these measures?
Can I speak to that? Just a second. I think I've got my little thing on here, just so we don't have to pass it around quite so much. I think the largest barrier to this was to know it's possible. And I think that's something that I mean all of us, all the people that have helped with this, have said it is possible to do this. And we've seen it happen in other places, and we can go there and we can look at those things. So the next barrier is tradition. And it's ruthless in big hospitals because of risk and fear of change, you know. So you get a litigation environment which says if there's a change in a hospital and there's something that goes wrong, it could be related to that change. So that slows change hugely by a leadership level in hospital systems, potentially, which works its way down into the facilities operations staff leadership, which then say, well, we worked with certain mechanical engineers, they know this building inside and out, and therefore you might have your hotshot Atelier 10 engineer over here, but you know, we have our so-and-so engineer that has worked in this building for a long time and has done a good job for us. And they probably have. But this is a change environment. And so that difficulty in helping everyone make that change is really, in a risky environment, is very, very hard. And so it takes local leadership, like projects that are happening here that say, the CEO can say, well, why are we doing this? And it's amazing how fast everyone learns, you know, what they can do once somebody's taken that leadership, like partners, obviously.
Also, regulation as well. Stretch code community. If you want to build a new building, you have to beat the code by 20% and the cost of energy. We do see our biggest challenge is the first cost, to us always. First cost, you know, energy efficiency, usually seen as mysterious and non-existent, and even with energy models and our incentives, they usually go on the side, and that's usually what we see as a problem. Yes.
Well, I guess I'm looking at that, and the issue of the increased design costs, increased construction costs, we're looking at facilities that have a long length of use. Has there been any sort of financial model to take those energy savings and seeing what the ROI is on that increased construction cost as a means of sort of dissolving those concerns on the climate?
We do it all the time, but still, you know, the paybacks are there. I mean, we're in with N-Star, and we can tell you the price of electricity is going to go up. I cannot tell you for what, but they understand that.
But I mean,
Yeah.
the means of the company,
Yes.
the great research that's already been
Yeah.
done, that sort of risk piece.
Mhm.
And saying, okay, I'm investing that 6%,
Mhm.
what am I getting?
Yeah.
And it's inevitably going to come down to a lot of times the dollar to the dollar.
It is, you know, and that's again the first cost, and we see it actually. David and I, we partner in a couple of projects, and you'll be surprised. I mean, it's palpable. You can show the numbers, you know, other than, you know, writing a contract with them, but it's a first cost many times, and depending, is the owner building their own buildings, or is somebody else building the building for them? And that's another big difference. You were mentioning that who is actually owning the building, who's going to pay for that for the life as well.
So everyone heard what the question was, is siloing of capital versus operations, you know, and certainly we see it in many other institutions in healthcare. But I think one of the things that is really interesting to us is where we have found healthcare systems around the country, Kaiser, Providence in the West, that set aside capital to invest in the capital cost of construction that is related to energy efficiency. So they set aside 3%. Total construction costs, they take 3% of the total construction costs and set it aside for energy efficiency. And they do that because they want to invest in things that pay back, what is it, less than 5 years, I think, right?
Yeah.
And
I think Providence, I think it's 1.5%, or yeah, 1.5% of the project cost, the total cost they set aside. And if the energy efficiency improvements pay back within 5 years, they'll put in that incremental 1.5% into the project.
And Kaiser's certainly doing that too. So it's just within the system that they have to realize that they have to make those investments. I bet partners could speak to that.
Yeah, and I think in one respect too, a lot of the consideration is on a planning level at this point. That's why so many institutions are doing cogen, big projects, lots of investment, looking down to recoup those costs, those operating costs over 20, 30, 40, 50 years beyond, but not considering it on the building end, which is an important part of this research. Is you can keep doing cogen, you can keep doing efficient central plants, but are you just putting more water in a leaky bucket already, the buildings being the leaky buckets? So that's the parts that we also need to tighten up.
Just to give you a sense of how Partners thinks in terms of payback, we have a strategic energy master plan for our buildings. We've got about 10 million square feet of owned buildings. And that's basically divided into 3 phases according to technologies, really. First phase, we get a 25% reduction just by energy conservation measures, fairly simple stuff. And we're getting between 3 and 5 year paybacks on that, on a $60 million investment. Then we get down to about 43, 44% in phase 2 with the use of installation of cogen. And typically the payback period is around 8 years on that. And then, so that brings us down to about, as I say, 44% reduction, which brings us into the, down to the Massachusetts Green Communities Act curve. But then we sort of run out of steam because phase 3 is alternative fuels. And at the moment, alternative fuels just do not pay for themselves. I mean, it's 20 to 40 years is the payback on that. And we can't afford it. We have very slender profit margins, sort of about 2%, even on a good year. And with the healthcare environment the way it is at the moment, nobody's willing to risk such a long-term investment with such a long payback.
So one of the things that got asked earlier about the sort of economics of all of this, I think the Northwest Energy Efficiency Alliance and their program Better Bricks, which funded a lot of our work, they developed a whole strategic energy management planning group of consultants that worked with hospital organizations to look at the financial questions. And what they were able to convince CEOs, CFOs, was that right now you're operating at a 2% profit margin or net operating income. So that means you have to take $50 to make $1. And so if I can invest $20 and make $1, in building efficiency, why would you do that in terms of profitability than invest $50 in that MRI or that new, building over here or this new set of surgery suites that is supposedly going to bring in this gross income? So if you go to the Better Bricks website and look for the sort of ownership side arguments in strategic energy management planning, I think you'll find them very compelling. And they're financial arguments that I'm otherwise uncomfortable making, but they've been very effective in the Pacific Northwest with big hospital organizations, Swedish, Providence, Kaiser, Group Health. Yeah. And one other thing that's interesting is we talked about barriers. I think, this is my optimistic side, there are incredible opportunities here. This is a very stressed healthcare world and a very stressed architecture and engineering world. So it's a time when we all can look for opportunities to differentiate ourselves and to make ourselves look and act more related to these individual markets. And being concerned with not only how a building is designed, whatever the heck that means, and we sort of throw the keys over the over the fence when we're done and walk away. If architects and the architects and engineering community can become concerned about operations and enter into this conversation with the owners on a continuous quality management vocabulary about setting goals early, testing for those goals throughout the process, and checking to see how you've met those goals in operations. The owner is quite likely to see a really unique delivery system here that is concerned about not only how it's designed, but how it actually operates, and then has fed back the successes and failures in that to improve the quality of production. You know, these are things that hospital systems thoroughly understand related to the Toyota way and all the various, you know, continuous quality improvement methods. And so it's a vocabulary that we're speaking to right here that is really capable of giving architects and engineers a unique, marketable vocabulary to function within, I think.
Yeah, I was going to ask, I was very curious, especially if you're to Europe, at the kind of operational level, the patient and nurse level, are there any operational impacts or challenges to this strategy? Or things that you think people in the U.S. wouldn't be used to doing with this strategy?
Sure. So the question was operationally at the patient or nursing level, in the Scandinavian examples, if there are big differences that might present barriers. I think it's a complex question. My mind is going through a list of them. But I think, kind of zooming out a little bit, there's interest from Scandinavia to look at the U.S. examples of patient room design, and especially single patient rooms. And that's, like in the new Karolinska Solna, that's primarily what they're going to have. And I think we're interested in the overall massing and energy use, so there's kind of cross-cultural collaboration that can happen there. There are definitely differences in, like, if you go to the one patient suite to another, for just a simple example is food is a very important part of the culture in Scandinavia, and having lunch together. And so just halfway down the corridor, there's always a break space that's for the family, the patient, the staff. It lengthens the corridor, but they have that social space that's important for them. Similarly, nursing stations have to have a window. So they are often distributed nursing stations along the corridor with either a skylight or relight or window. So there are definitely differences, but I think there are things that we can look back and forth to improve both sides of the coin.
No, it's good.
So if there are any final closing comments or questions from anyone?
Can we ask about the chilled beans? Did you look at anything related? Because I am curious about that topic.
We had a project with ZGF that at Seattle Children's Medical Center, big patient tower, I think it was 180 beds, and an ED on the first floor. A large addition to an existing large hospital. And they were just on the cusp of accepting chilled beams. And it was just at the very end that infection control just put the hammer down and said, nope, not going to happen. So we certainly see chilled beams in lab buildings all over Seattle. So this is not an uncommon thing. And through our connection with Perkinsville, we understand I think it's more than a rumor, but the general...
Yep, there's a hospital being constructed right now in North Carolina called Moses Cone that will have radiant ceiling chilled beams.
Active chilled beams. The issue at Children's was they were just concerned about infection control on the potentially chilled surfaces, picking up dust, and then maybe a little condensation. And, you know, and we went through a huge process of looking at this in a new lab building for the University of Washington, where there were full-scale mock-ups built and the little convection currents that have developed that don't allow condensation to happen, even at temperatures you'd expect them to occur. And they were just a little too nervous. So it's about to happen. It's
I think going back to one of the first questions of like, why isn't this happening? It seems really compelling from your comment. And when we went to each of our cities and talked with people, that was one of our questions. What are barriers and how do we overcome them? And one of the big ones that we heard is the lack of built precedents. And so we're interested in implementation, seeing it happen and also documenting those examples so we can all look to them as evidence to show this is possible here in the U.S.
We are currently in the design process of a large new hospital, and they are considering that actually. So this is something that will happen maybe 3 years down the line, but they're thinking about it. I can't tell you who, but it's moving along.
Right. So the question is there interest in creating a Target 100-like roadmap and development of precedents for deep renovations and potentially tapping into the Clinton Climate Initiative kind of trajectory for that? And the short answer is we are very interested in developing that. I think there's a lot of interest and there's a lot happening in renovations, and I think a guide for that, I see nodding heads, would be helpful. We've focused on new construction so far, but our goal is to try to do that.
The new construction is so simple. It's so hard. It's really hard, but it's so simple in comparison to existing buildings. And we've been doing, again, funded by Better Bricks, a process of looking at large commercial real estate buildings and the deep renovation of those, including 50% plus better efficiency below where the current energy use is. And like in all of these, you learn from that process of the last 2 years and see how it could apply to hospitals and a lot of other buildings. And the bottom line is these little efficiency improvements, like 5 and 10%, are just killing the ability to do deep renovations. So our market for, let's say, large commercial real estate buildings is that we know these buildings were constructed before 1990, really before the energy code had much effect. And they were constant air volume systems. They might, in the Northwest, they're commonly all electric. I mean, they have the most giant electric boilers with toggle switches on them. It's the craziest darn thing. Pneumatic controls. You're looking for buildings where none of that has been updated. Probably have updated the lighting a little bit. And when you find buildings like that, man, there's a huge opportunity there. But the wall that you're talking about that you've run into is the envelope and all the stuff that is expensive to replace and the cost. So you can take that cost out. Same thing is true in healthcare, that if you're doing a large update of a building and you really want it to look a little different than something that was built in 1927 or 1985, then you can get into the envelope, which is where you can get the load reduction, the peak load reduction. You can change systems. Other exciting thing is these systems fit into lower floor-to-floor heights. These are, when we're talking about going to fan coil units or radiant ceilings, we're talking about piping heat and cool around the building. It takes a lot less space, and that's what a lot of these buildings were designed to operate with prior to 1970. So we think a lot of these systems can fit fairly well into existing buildings at probably a cost of half what a new construction would be. Now there's this question of medical planning and how that's changed and whether you want to stick with that old building or not, but that's something else. Other thing is we've discovered floor by floor renovations. We were just looking at a Perkins Will office renovation in a historic building downtown Seattle where the whole building EUI was 120. And they just decoupled their floor entirely from the building systems. And the EUI for their floor, it's all electric, is 40. And we're like, how did that happen? And you look at it, and they just took out a floor, decoupled the ventilation, heating, and cooling systems, put in operable windows, really carefully look at the plug loads, and they've, You know, they reduced the whole building EUI by roughly 25% by doing a floor. And we think that there's an opportunity potentially of doing floor-by-floor retrofits, deep retrofits of hospitals where you look at decoupled and decentralized ventilation systems which don't depend on the central plant.
Thank you. Well, I'd like to encourage everyone, if they have additional questions,
That's a mouthful.
or great panelists, David Belko, Carlos Niemeyer, Ben Shepard, or Hubert Murray, to ask away in the reception in the gallery. And I'd like to again thank the BSA Healthcare Committee and the BSA Committee on the